So the last type of frequency meter that we'll be studying is the saturable core frequency meter. The construction of this frequency meter looks something like this. This here shows the saturable core frequency meter. The main elements of this frequency meter, the main element itself is the saturable core transformer. You have the bridge rectifiers, the meters, and the primary detecting element in this meter is actually the transformer itself. So this core assembly basically will consist of three parts itself. You have the outer core, that's actually the magnetic material, and the outer core is of a larger cross-sectional area. Now this large area means no saturation, no magnetic saturation. So you have the outer core that's made up of the magnetic material, and it will not saturate because of the large cross-sectional area. Then you have this leg of the transformer, that's the leg A, and this will be a non-magnetic material. Fine. And similarly the leg B, but this leg B will be a magnetic material. And you have windings, that's actually the primary winding and the secondary windings that will be wound around these legs. So you have the outer core made up of the magnetic material of a large cross-sectional area so that it does not saturate easily, and the leg A of this transformer is non-magnetic, while the leg B of this transformer is magnetic. As far as the cross-sectional area of A and B goes, they are of same cross-sectional area. And the thing about this leg B is, since it will saturate easily as compared to the core of the transformer, the outer core of the transformer, this magnetic leg B will saturate. So what is the principle of operation is that you have the windings wound around these legs A and B. The primary winding is wound around both legs A and B, whereas the secondary winding is broken up into two different coils, and one coil will be wound around leg A, while as the second coil will be wound around leg B. Fine. So the input primary winding is wound around both legs, leg A as well as leg B, same coil, while as secondary winding it actually is two different coils. They are not one coil. Both the coils, one will be wound around leg A, and the second one will be wound around the leg B of the transformer, of the legs of the transformer. Also to note here that these two coils will be in series with each other, and the important thing is that they will be wound around these legs in such a fashion that the EMF generated in these two coils, EMF generated in coil A and in coil B, EMF induced rather, coil A and coil B, will oppose each other. So the secondary coil is wound around in such a fashion around leg A and leg B, such that the EMF induced in the two coil segments will oppose each other. So what happens is, as we achieve saturation, uh, induced voltage will increase in coil A at the same rate as the induced voltage will increase in the secondary coil uh, wound over the leg B. Fine. So you have two coils. One is around leg A, another one is around leg B, secondary coils. So the rate of voltage being induced in coil in leg A, coil of leg A will be same as the rate of induced voltage in the coil of leg B. So what happens is the rate of increase will also cancel out each other. So now the secondary output voltage is no longer the function of the primary voltage. It will not depend upon the primary voltage of the transformer, but it will be a function of the frequency only. Let's see this mathematically. If phi is the difference, this phi here is the difference of flux we know E is equal to induced EMF is equal to N d phi by dt, where phi here is the difference, or you can say the total magnetic flux linkage, the net magnetic flux linkage on the secondary coil side. So difference between the fluxes of leg A and leg B. E is equal to N d phi by dt. So what we can say is that average voltage over a half cycle on the secondary side, E average will be equal to omega by pi 0 to the average voltage per half cycle will be omega by pi integration over 0 to pi by omega, and this means for an f phi m, or we can also say frequency will be equal to E divided by 4 n phi m. So we already know the equation of a transformer is E is equal to 4.44 N phi Fm. So we are just proving that, but what we have to see here is that this flux here phi is not actually the flux, the total flux being linked with the secondary coil segment, but it is the difference between the flux linking the coil segment A and the coil segment wound around the leg B. So your frequency from this very circuit will be equal to E divided by 4N phi Fm. So if we can calibrate our device for measurement of this frequency, the deflection, we know now that I is directly proportional to, we have the rest of the circuitry as well. So I will be proportional to, or you can simply say EAV divided by R, while as the deflection theta is directly proportional to IAV, but since EAV is proportional to frequency, so you can say IAV in other words is proportional to frequency, or in other words you can say theta is proportional to the frequency of the supply voltage. So thus the deflection theta is directly proportional to the current IAV that is detected by the permanent magnet moving coil instrument. Fine. So you actually now, once you have the transformer, we have seen at the output of the transformer the voltage, induced voltage, is directly proportional to the frequency. Now this voltage is actually setting up a current in this, because there is a resistor and a rectifier also attached here. So the PMMC will actually be measuring only the DC currents. The rectifier will convert this AC voltage into DC voltage, so a DC current will be flowing through the PMMC. This average voltage, now this current, average current flowing through the PMMC is proportional to EAV divided by R, and in other words you can say, since EAV is proportional to frequency, IAV is proportional to EAV, IAV is proportional to frequency, and we know that the deflection theta that will be caused in the permanent magnet moving coil instrument, the meter, will be proportional to the current itself. So in other words, theta here is now proportional to the frequency of the supply voltage. So this type of frequency meter helps us calculate frequencies over a wide range of spectrum. So that's about the frequency meters. We have studied various types of frequency meters: the mechanical resonance type, the electrical resonance type, in which we study the ferrodynamic type. We then studied the electrodynamometer, type. We studied the Western type. We have studied the ratiometer type and the saturable core type transformers. So in the saturable core type transformer, what we do is we are using a transformer with two coils wound around two different legs of the secondary coil segment, and they are wound in such a fashion that the output voltage on the two coil segments will oppose each other. So the total flux generated, the total flux linking the secondary coils will be different. Now we also need to note here that the output voltage of the transformer at saturation will be derived as per the equations given there. E average will be equal to N 4N F phi m, where a phi m is the maximum flux linking the coil segments, coil A and coil B. So accordingly, after rectification, we can understand that the current that will cause the deflection in the permanent magnet meter, PMMC meter, will actually be proportional to the applied frequency. So with this we conclude the frequency meters. We have other types of devices that can be used for measurement of phase, like the synchronous scopes. Again, there are different types of synchronous scopes. We have the Western type synchronous scope, and it has a similar almost a similar principle like that of the Western type frequency measurement device. And we have a moving iron synchronous scope. That is not actually nothing but the Nelder-Lipman type synchronous scope. We have also studied the Nelder-Lipman type phase measurement. So this particular device can be used for measurement of phase and frequency, and also synchronizing between the alternators or extra. We also have the phase sequence indicators. The phase sequence indicators, again, they can be used for indication of phase of three-phase circuitries, and so we can actually say what is whether we have an ABC phase or we have a ACB phase. We can determine that using the phase sequence indicators. So we'll wrap up this chapter and we'll start with the data acquisition systems in the next session.